Subscribe so you don't miss out on any of these videos. The universe, vast and incomprehensible, stretches beyond the boundaries of human understanding. For millennia, humans have gazed up at the night sky, pondering the mysteries that lie beyond the stars. Even with all of the scientific advancements we've made, the universe remains a deep well of unknowns, teeming with questions that have yet to be answered. From the enigmatic black holes that warp space and time, to the elusive dark matter that makes up most of the cosmos, the mysteries of the universe are as profound as they are numerous. One of the most profound mysteries is the origin of the universe itself. The prevailing theory, the Big Bang, suggests that the universe began as an infinitely small, infinitely dense point around 13.8 billion years ago. This event marked the beginning of time and space, but what existed before the Big Bang? Was there anything at all? And if so, how could something exist before time itself? This paradox challenges our fundamental understanding of existence and pushes the boundaries of both science and philosophy. Additionally, what caused the Big Bang? The idea of a universe suddenly springing into existence from nothing defies intuition, yet it's the best model we have for explaining the cosmos. The question of why the universe exists, or why there is something rather than nothing, remains one of the most profound mysteries. Expanding outwards from the origin of the universe, we confront the question of its ultimate fate. Will the universe continue to expand forever, or will it eventually collapse back in on itself in what is sometimes called the Big Crunch? Alternatively, could the expansion of the universe continue to accelerate until galaxies drift so far apart that the stars burn out, leaving a cold, dark, and empty cosmos, a scenario known as the Big Freeze? There's even the possibility of a Big Rip, where the accelerating expansion of the universe tears apart not only galaxies and stars but atoms themselves. The ultimate fate of the universe is intimately tied to the properties of dark energy, a mysterious force that seems to be driving the acceleration of cosmic expansion. Yet, we know almost nothing about dark energy. What is its nature? Is it a constant force, or will its properties change over time? Could it be linked to the quantum realm, or is it something entirely different? Dark energy is a complete enigma, one that could hold the key to the universe's ultimate destiny. Just as perplexing as dark energy is dark matter. Observations of galaxies and galaxy clusters indicate that the visible matter we can see, stars, planets, gas, and dust, accounts for only a small fraction of the universe's total mass. The rest, around 85%, is invisible and undetectable by conventional means. We call this unseen substance dark matter, but we have little idea of what it actually is. It doesn't emit, absorb, or reflect light, making it impossible to observe directly. We can only infer its presence through its gravitational effects on visible matter. But what is it made of? Some scientists suggest it could be composed of exotic particles that don't interact with normal matter in the usual ways. Others propose that dark matter might be related to new, undiscovered dimensions or other phenomena that go beyond the standard model of physics. Whatever it is, dark matter plays a crucial role in shaping the large-scale structure of the universe, influencing the formation of galaxies and galaxy clusters. Yet, despite its importance, it remains one of the most elusive puzzles in modern astrophysics. The mystery of black holes adds yet another layer of intrigue to the cosmos. These strange objects, formed from the remnants of massive stars, possess such intense gravitational pull that nothing, not even light, can escape from them once it crosses the event horizon. This makes black holes essentially invisible to direct observation, yet they exert a powerful influence on their surroundings. The core mystery surrounding black holes is their very nature. What happens to matter that falls into one? According to Einstein's theory of general relativity, the mass and energy of objects consumed by a black hole should be compressed into a singularity, a point of infinite density and zero volume. But the laws of quantum mechanics, which govern the behavior of particles at the smallest scales, break down in the face of such infinities. This has led to a major unresolved conflict between general relativity and quantum theory, with black holes sitting at the center of this cosmic dilemma. In recent years, some scientists have proposed that information consumed by black holes is not lost, but somehow encoded on the event horizon, a concept known as the holographic principle. Yet, this theory remains speculative, and black holes continue to defy our attempts to fully understand them. Another curious aspect of black holes is their role in the growth of galaxies. At the heart of most galaxies, including our own Milky Way, lies a supermassive black hole millions or even billions of times more massive than the Sun. These black holes are thought to play a crucial role in the formation and evolution of galaxies. But exactly how this process works is still not fully understood. Did supermassive black holes form first, acting as seeds for the growth of galaxies? Or did galaxies form first, and supermassive black holes developed as a consequence? The relationship between galaxies and black holes is one of the biggest puzzles in astrophysics today, and studying this connection may yield clues about the fundamental forces that shape the universe. Moving beyond black holes, we encounter the perplexing phenomenon of time. In everyday life, time flows in one direction, from the past through the present and into the future. This is what scientists call the arrow of time. But on the microscopic scale of quantum mechanics, time appears to be reversible. The equations that describe the behavior of particles work equally well whether time is running forwards or backwards. So why do we experience time as moving in one direction? One explanation lies in the concept of entropy, a measure of disorder in a system. According to the second law of thermodynamics, entropy tends to increase over time, which gives rise to the arrow of time. However, the question remains, why did the universe start in a state of low entropy? What mechanism set time on its one-way path? Moreover, if time is fundamentally reversible at the quantum level, could it be possible to manipulate or even travel through time? While the idea of time travel has been a staple of science fiction for decades, some physicists believe it could theoretically be possible under certain conditions, though the practical challenges involved are staggering. Another tantalizing mystery of the universe is the possibility of parallel universes or alternate dimensions. In the standard model of physics, we inhabit a universe with 3 spatial dimensions and 1 time dimension. But some theories, such as string theory, propose the existence of additional dimensions beyond the ones we can perceive. These extra dimensions could be compactified, meaning they are curled up so tightly that they are effectively invisible at our scale. Alternatively, they might be vast, separate realms that exist alongside our own. Some scientists have even proposed that our universe could be just one of many in a multiverse, with each universe having different physical laws and constants. If this is true, then the universe we observe is just a small part of a much larger, more complex reality. However, the idea of a multiverse is speculative and difficult to test experimentally. If these parallel universes exist, they may be forever beyond our reach, existing in dimensions or realities that we cannot access. Yet, the multiverse hypothesis opens up fascinating possibilities. Could there be alternate versions of ourselves in other universes, living out different lives under different circumstances? The multiverse concept also raises profound questions about the nature of reality itself. If multiple universes exist, each with its own distinct physical laws, what determines the fundamental properties of our universe? Is our universe special? Or is it just one of countless variations in an infinite cosmic landscape? Some versions of the multiverse theory suggest that every possible outcome of every event actually occurs, but in a different universe. This leads to the idea of quantum branching, where every decision we make creates a new, parallel universe. For example, in one universe, you might decide to turn left, while in another you turn right, each choice spawning a new reality. This theory, while highly speculative, forces us to reconsider the nature of free will and determinism, suggesting that every possibility is realized somewhere in the multiverse. Speaking of possibilities, one of the most fundamental mysteries of the universe is the existence of life itself. How did life arise from non-living matter? The origin of life on Earth remains a topic of intense scientific inquiry, but it is also shrouded in mystery. While scientists have made progress in understanding the conditions that could have given rise to life, such as the presence of water, certain chemicals, and energy sources, the exact mechanisms that led to the first self-replicating molecules remain elusive. Moreover, Earth may not be unique in its ability to support life. With the discovery of thousands of exoplanets, planets orbiting other stars, it seems increasingly likely that habitable environments exist elsewhere in the universe. This brings us to the age-old question: are we alone in the universe? The search for extraterrestrial life has been ongoing for decades, yet despite our best efforts, we have found no definitive evidence of alien civilizations. This is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If the universe is teeming with stars and planets, and if life can arise under the right conditions, then why haven't we detected any signs of intelligent life? There are numerous possible answers to this paradox. One is that intelligent civilizations are extremely rare or short-lived, either because they are destroyed by natural disasters, self-destruction, or other factors before they can develop interstellar communication. Another possibility is that advanced civilizations are deliberately avoiding contact with us, perhaps following a form of cosmic non-interference directive, much like the Prime Directive in science fiction. Alternatively, we may simply be looking in the wrong place or using the wrong methods to search for extraterrestrial signals. Some scientists even propose that alien life could exist in forms so different from our own that we wouldn't recognize it if we saw it. Then there's the idea that we are living in a cosmic zoo, being observed by advanced extraterrestrial beings who have chosen not to reveal themselves to us. This is known as the zoo hypothesis, and it suggests that more advanced civilizations might treat Earth as a kind of nature preserve, watching us from afar while allowing humanity to develop naturally without interference. Another, even more speculative, theory is that we are living in a simulated universe, an idea popularized in recent years by philosophers and scientists alike. According to this theory, our entire reality, including the stars, planets, and galaxies, might be a highly advanced computer simulation run by some superintelligent entity. If this is true, it raises deep questions about the nature of consciousness, free will, and the purpose of existence itself. Could we ever escape the simulation or even prove that it exists? And if we did, what would that mean for our understanding of reality? On a more practical level, the mysteries of the universe extend to the forces and particles that govern the behavior of matter and energy. The standard model of particle physics describes the known particles and forces, but it is incomplete. For one, it does not account for gravity, the weakest yet most pervasive of the fundamental forces. While general relativity describes how gravity works on large scales, shaping the motion of planets, stars, and galaxies, it doesn't fit neatly into the quantum realm, where the other forces dominate. The search for a theory of quantum gravity, one that can unify general relativity with quantum mechanics, is one of the greatest challenges in modern physics. This quest has led to the development of various theories, including string theory and loop quantum gravity, but none have been proven yet. String theory, in particular, posits that the fundamental particles we observe are not point-like objects but rather tiny, vibrating strings. The different vibrational modes of these strings give rise to the various particles and forces. String theory also predicts the existence of additional dimensions, beyond the familiar 3 dimensions of space and 1 of time. These extra dimensions could be compactified or hidden from view, but they might play a crucial role in shaping the fundamental forces of nature. However, string theory remains controversial, as it is difficult to test experimentally. Without direct evidence, it remains an elegant but speculative framework for understanding the universe. Quantum mechanics itself is filled with mysteries. The famous double-slit experiment, for example, reveals the bizarre behavior of particles at the quantum level. When individual particles, such as electrons or photons, are fired through 2 slits, they behave like waves, creating an interference pattern on a screen behind the slits. But when scientists try to observe which slit the particle passes through, the interference pattern disappears, and the particles behave like solid objects. This suggests that the very act of measurement affects the outcome of the experiment, a phenomenon known as wave-particle duality. At its core, quantum mechanics challenges our classical notions of reality, suggesting that particles exist in a superposition of states until they are observed. This has led to the famous Schrödinger's cat thought experiment, in which a cat in a sealed box is both alive and dead until the box is opened and the cat's state is observed. This strange behavior at the quantum level raises deep philosophical questions about the nature of reality. What does it mean for something to exist if it only takes on a definite state when observed? Does reality depend on the observer, or is there an objective reality that exists independently of our measurements? Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that the wave function of a particle collapses into a definite state upon measurement. Other interpretations, like the many worlds interpretation, propose that every possible outcome of a quantum event actually occurs, but in separate, parallel universes. These ideas challenge our intuitive understanding of existence and force us to confront the possibility that reality is far stranger and more complex than we ever imagined. As we delve deeper into the mysteries of the universe, we also confront the enigma of consciousness itself. How does the brain give rise to subjective experience? What is the nature of the self? And how does it persist over time? While neuroscience has made significant progress in understanding the mechanisms of the brain, the hard problem of consciousness, the question of how and why we have subjective experiences, remains unsolved. Some scientists and philosophers propose that consciousness is an emergent property of complex neural networks, while others suggest that it might be a fundamental aspect of the universe, akin to space and time. This idea, known as panpsychism, posits that consciousness is a basic feature of all matter, and that even elementary particles might possess some rudimentary form of awareness. If true, this would radically alter our understanding of both the mind and the cosmos. The relationship between consciousness and the universe has fascinated both scientists and philosophers for centuries. Some have speculated that consciousness could play a more direct role in shaping the universe than we currently understand. Quantum mechanics, with its strange dependence on observation, has led some thinkers to wonder if consciousness itself might be a fundamental force in the cosmos. Could the act of observation actually bring reality into existence? This concept is sometimes referred to as the observer effect, where the presence of a conscious observer is thought to influence the outcome of quantum events. While this remains speculative and highly debated, it touches on the deep interconnectedness between the mind and the universe, which is a recurring theme in both science and philosophy. Beyond the mysteries of consciousness and quantum mechanics, the nature of time itself presents profound questions. Time, as we experience it, flows in one direction, from the past to the future. However, the laws of physics, especially those governing quantum mechanics and relativity, do not dictate a single direction for time. In theory, time could flow in reverse, and some interpretations of physics suggest that the arrow of time is not a fundamental feature of the universe but rather a byproduct of the increase in entropy. Entropy, which measures the disorder in a system, tends to increase over time, and this increase is often thought to be the reason we experience time as moving forward. But what if time is more flexible than we think? The concept of time travel, for instance, has been a subject of fascination for both scientists and science fiction enthusiasts. General relativity, Einstein's theory of gravity, allows for the possibility of time loops or closed time-like curves under certain extreme conditions, such as near black holes or wormholes. These solutions to Einstein's equations suggest that it might be theoretically possible to travel back in time, though practical constraints and paradoxes make it seem unlikely. The famous grandfather paradox asks what would happen if you traveled back in time and prevented your grandfather from meeting your grandmother, thus preventing your own birth. Such paradoxes challenge our understanding of causality and raise questions about the very nature of time and reality. Some theories suggest that time travel would simply create alternate timelines or parallel universes, allowing for changes in the past without affecting the present we know. Others propose that the universe has built-in mechanisms to prevent time travel paradoxes from occurring in the first place. Speaking of paradoxes, the measurement problem in quantum mechanics presents another enigma that connects time, observation, and reality. The act of measuring a quantum system seems to collapse its wave function, bringing the system into a definite state. But what constitutes a measurement? Does it require a conscious observer, or can inanimate objects, like measuring devices, cause wave function collapse? If consciousness is not required, then time itself might be more fluid than we imagine, with the act of measurement playing a crucial role in determining the past, present, and future. Some physicists have even proposed retrocausality, the idea that events in the future could influence the past, flipping our conventional understanding of cause and effect. Time dilation, a well-documented phenomenon in relativity, also challenges our intuitive grasp of time. According to Einstein's theory of relativity, time is not an absolute, constant entity but rather is affected by both speed and gravity. The faster an object moves, or the closer it is to a strong gravitational field, the more time slows down for that object relative to an outside observer. This has been confirmed by experiments, such as those involving highly accurate atomic clocks on airplanes or satellites, which experience slightly slower time compared to clocks on Earth. But the implications of time dilation go beyond mere technicalities. They suggest that time is deeply intertwined with the fabric of space itself, forming the four-dimensional continuum we call spacetime. This brings us to one of the greatest mysteries in physics, the nature of spacetime itself. Einstein's theory of general relativity describes how massive objects warp spacetime, creating the force we perceive as gravity. But what is spacetime exactly? Is it a real, physical entity, or is it simply a mathematical framework for describing the behavior of objects in the universe? The concept of spacetime leads to even deeper questions about the nature of the universe's structure. Could spacetime be quantized, made up of discrete units, much like matter is made of atoms? This is one of the central questions in the quest for quantum gravity, a theory that would unify general relativity and quantum mechanics. Some approaches to quantum gravity, such as loop quantum gravity, propose that spacetime itself is composed of tiny, indivisible loops, each representing a quantum of space. Other approaches, like string theory, suggest that the fundamental building blocks of the universe are not particles or loops but tiny vibrating strings, with spacetime emerging from the interactions of these strings. If spacetime is quantized, it could mean that the smooth, continuous fabric we perceive is an illusion, and that at the smallest scales, the universe is composed of discrete chunks of space and time. The fabric of spacetime is not only shaped by massive objects, but can also be distorted in other ways. For instance, black holes, regions of space where gravity is so strong that not even light can escape, represent a dramatic warping of spacetime. Inside a black hole, spacetime becomes so curved that all paths lead to a single point known as a singularity, where the laws of physics as we know them break down. The singularity represents a mystery at the heart of black holes. What happens to matter and information that falls into a black hole? According to classical physics, information should be lost forever in the singularity, but this violates the principles of quantum mechanics, which dictate that information cannot be destroyed. This leads to the black hole information paradox, a puzzle that has baffled physicists for decades. Some theories suggest that information is preserved on the event horizon, the boundary of a black hole, while others propose that black holes might eventually evaporate through a process known as Hawking radiation, releasing the information back into the universe in a scrambled form. Resolving this paradox is key to understanding the relationship between quantum mechanics and general relativity, and it may hold the key to a deeper understanding of the universe's most extreme environments. But black holes are not the only strange objects that warp spacetime. Wormholes, hypothetical tunnels through spacetime, are another possibility predicted by general relativity. A wormhole could theoretically connect two distant regions of the universe, allowing for faster-than-light travel. In essence, a wormhole would act as a shortcut through spacetime, enabling travelers to bypass vast distances instantaneously. While no evidence for wormholes has been found, they remain a tantalizing possibility in both science fiction and theoretical physics. Another profound mystery related to spacetime is the concept of the Big Bang, the event that marked the beginning of our universe. According to the Big Bang theory, the universe began as a singularity, a point of infinite density and temperature, before rapidly expanding and cooling to form the galaxies, stars, and planets we observe today. But what caused the Big Bang? And what, if anything, existed before it? The standard model of cosmology suggests that time and space themselves began with the Big Bang, meaning that there may be no before. However, some theories, such as the cyclic universe or the multiverse, propose that our universe is just one in a series of cosmic cycles, or that it arose from a larger multiverse. In the cyclic model, the universe undergoes repeated cycles of expansion and contraction, with each Big Bang followed by a Big Crunch, in which the universe collapses back into a singularity before exploding again. This theory avoids the need for a singular beginning to time, but it also raises questions about the ultimate fate of the universe. Will it continue expanding forever, or will it eventually collapse back on itself? Observations of distant galaxies suggest that the universe's expansion is accelerating, driven by a mysterious force known as dark energy. Dark energy is one of the greatest mysteries in modern cosmology. Discovered in the late 1990s, it accounts for roughly 70% of the universe's total energy density, yet its true nature remains elusive. Unlike dark matter, which interacts with gravity but not with light, dark energy is thought to be responsible for the accelerated expansion of the universe. The discovery of this accelerating expansion upended the traditional view that gravity should gradually slow the universe's expansion over time. Instead, distant galaxies are moving away from us faster and faster, suggesting that dark energy is exerting a repulsive force on the fabric of spacetime. What exactly is dark energy? Some physicists believe it could be a property of space itself, an intrinsic energy that increases as the universe expands. Others propose that dark energy might be related to a new, unknown field or force. There is even the possibility that dark energy could be a sign that our understanding of gravity is incomplete. Modified theories of gravity, such as those that extend or alter Einstein's general relativity, might provide an explanation for dark energy's effects. However, none of these theories have yet been confirmed, and dark energy remains one of the most profound and unsolved mysteries of the cosmos. The fate of the universe is intimately tied to the nature of dark energy. If dark energy continues to dominate the universe, the expansion may accelerate indefinitely, leading to a big freeze, or heat death. In this scenario, galaxies would drift farther apart, stars would burn out, and the universe would eventually become a cold, dark, and lifeless void. Alternatively, if dark energy behaves differently over time, it could lead to a big rip, in which the expansion becomes so extreme that even atoms and subatomic particles are torn apart. On the other hand, if dark energy reverses its effect or decays over time, the universe could eventually collapse in a big crunch, leading to the cyclic universe scenario mentioned earlier. Dark energy is not the only cosmic mystery that challenges our understanding. Dark matter, another elusive component of the universe, accounts for about 27% of the total mass energy content of the universe. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. Its presence is inferred from its gravitational effects on galaxies and galaxy clusters. Without dark matter, the rotation of galaxies and the behavior of galaxy clusters cannot be explained. Dark matter holds galaxies together, providing the extra mass needed to prevent them from flying apart as they spin. But what is dark matter made of? Despite decades of research, scientists have yet to directly detect dark matter particles. Leading candidates for dark matter include WIMPs, weakly interacting massive particles, axions, and sterile neutrinos. Each of these hypothetical particles has unique properties that could explain dark matter's behavior, but none have been confirmed. Experiments around the world are attempting to detect dark matter particles through their rare interactions with normal matter, but so far, the search has yielded no definitive results. Dark matter could also be more exotic than we imagine, perhaps composed of particles that do not fit within the standard model of particle physics, or it could be a manifestation of new forces or dimensions. The mystery of dark matter also connects to questions about the large-scale structure of the universe. Galaxies are not evenly distributed throughout space but instead form vast, interconnected webs of matter, with clusters of galaxies connected by filaments of dark matter. This cosmic web is thought to have formed due to the gravitational influence of dark matter, which helped to shape the early universe and guide the formation of galaxies and galaxy clusters. Studying the cosmic web provides insights into the distribution of dark matter and the evolution of the universe, but it also raises questions about how such a structure came to be and what role dark matter plays in shaping the universe. As we explore the mysteries of dark matter and dark energy, we are also confronted with the enigma of the universe's beginning. The Big Bang Theory describes how the universe expanded from an incredibly hot, dense state, but it does not explain what caused the Big Bang or what preceded it. Some physicists speculate that the Big Bang could be the result of a quantum fluctuation, a random event in which energy from the quantum vacuum created a rapidly expanding universe. Others propose that our universe could be part of a multiverse, a vast collection of universes, each with its own laws of physics and initial conditions. The multiverse theory offers intriguing possibilities for the origin of our universe. According to some interpretations of quantum mechanics, every possible outcome of a quantum event occurs in a separate, parallel universe. This idea, known as the many worlds interpretation, suggests that there could be an infinite number of universes, each representing a different outcome of every quantum event. In this scenario, the Big Bang could be just one of countless Big Bangs occurring in an infinite multiverse. Another version of the multiverse theory arises from the concept of cosmic inflation, a rapid expansion that occurred in the first fractions of a second after the Big Bang. According to inflationary theory, the universe underwent a period of exponential growth, driven by a high-energy field. After inflation ended, the universe continued expanding at a slower rate. However, some versions of inflationary theory suggest that inflation never truly ends and that different regions of space continue to undergo inflation at different rates. This leads to the idea of an eternal inflation multiverse, in which new universes are constantly being born in an ever-expanding cosmic landscape. The multiverse theory is controversial, as it suggests the existence of universes that are inherently unobservable. If other universes exist beyond the reach of our telescopes, can they ever be studied scientifically? Some physicists argue that the multiverse is a natural consequence of certain theories of physics, while others contend that it ventures into the realm of metaphysics rather than science. The debate over the multiverse touches on fundamental questions about the nature of reality, the limits of human knowledge, and the role of observation in determining the nature of the universe. One of the strangest aspects of the universe is the fine-tuning of its physical constants. The values of fundamental constants, such as the strength of gravity, the charge of the electron, and the speed of light, are remarkably well suited to allow the existence of life. If any of these constants were even slightly different, stars might not form, atoms might not hold together, and life as we know it would be impossible. This fine-tuning has led to speculation that the universe might be designed to support life, a concept known as the anthropic principle. The anthropic principle comes in two forms, the weak anthropic principle and the strong anthropic principle. The weak version simply states that we observe the universe to be fine-tuned for life because we exist to observe it. In other words, if the universe were not hospitable to life, we would not be here to ask the question in the first place. The strong version, however, suggests that the universe is not just coincidentally fine-tuned for life but may have been purposefully designed or constrained to allow life to exist. The fine-tuning of the universe has led some to speculate about the existence of a multiverse, in which different universes have different physical constants. In this view, our universe is just one of many, and we happen to live in a universe with the right conditions for life. While the fine-tuning argument remains speculative, it raises profound questions about the nature of the universe and our place within it. The fine-tuning of the universe also intersects with the question of why the universe appears to be so well-ordered. From the orbits of planets to the behavior of subatomic particles, the universe follows predictable laws of physics that can be described mathematically. This orderliness is not something we take for granted, but rather it is a deep mystery of the cosmos. Why does the universe follow mathematical rules? And why do these rules allow for the complexity and diversity we see today? One explanation is that the laws of physics are a natural consequence of the underlying structure of the universe. The mathematical laws that govern the universe may be an expression of deeper symmetries or principles that dictate how matter and energy behave. For example, the laws of conservation, such as the conservation of energy, momentum, and charge, can be understood as a consequence of the symmetries of spacetime. In this view, the universe's orderliness is an inevitable result of its underlying structure, much like how the patterns in a crystal emerge from the arrangement of its atoms. But there are other, more philosophical questions at play. Why should the universe be comprehensible at all? The fact that we can describe the universe using mathematics and logic raises profound questions about the relationship between human cognition and the cosmos. Is the order we observe in the universe a reflection of its true nature, or is it a construct of our minds, imposed on a fundamentally chaotic reality? Some philosophers and physicists argue that the human mind evolved to recognize patterns and regularities in nature because doing so was advantageous for survival. From this perspective, the universe may not be inherently orderly, but our minds perceive it as such because we are wired to look for order. Another profound mystery of the universe is the question of time. Time is one of the most fundamental aspects of our experience, yet its true nature remains elusive. In classical physics, time is often treated as a simple, linear progression, flowing from the past to the future. However, in the context of modern physics, time behaves in much more complex and puzzling ways. Einstein's theory of relativity revealed that time is not an absolute, unchanging backdrop to events, but rather it is intertwined with space to form spacetime. In relativity, time can stretch or contract depending on the observer's motion and the presence of strong gravitational fields. This effect, known as time dilation, has been confirmed through experiments and observations, such as those involving fast-moving particles or clocks placed at different altitudes. But the implications of relativity go even further. At the speed of light, time effectively stops. This suggests that for photons, the particles of light that travel at light speed, time is meaningless. How do we reconcile this with our everyday experience of time? The question of time becomes even more mysterious in the realm of quantum mechanics. In quantum theory, particles exist in a state of superposition, meaning they can occupy multiple states simultaneously until observed. This creates a puzzling relationship between time and measurement, leading to strange phenomena such as quantum entanglement, where two particles can influence each other instantaneously, even when separated by vast distances. This spooky action at a distance, as Einstein called it, appears to violate the idea that information cannot travel faster than light, leading to paradoxes about the nature of time and causality. Time also plays a central role in the puzzle of entropy and the arrow of time. According to the second law of thermodynamics, the entropy, or disorder, of a closed system tends to increase over time. This gives rise to the arrow of time, the perception that time flows in one direction, from past to future. But why should this be the case? The laws of physics are mostly time-symmetric, meaning they do not distinguish between past and future. In principle, time could flow backward just as easily as it flows forward, yet we observe time as moving inexorably in one direction. Some physicists suggest that the arrow of time is linked to the initial conditions of the universe. In the moments after the Big Bang, the universe was in a state of extremely low entropy, and ever since, it has been moving toward higher entropy. But the deeper reason why the universe started in such a low entropy state remains a mystery. The mystery of time also intersects with questions about the nature of black holes. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. At the center of a black hole lies a singularity, a point where spacetime curvature becomes infinite and the known laws of physics break down. One of the great unsolved mysteries of modern physics is how to reconcile the behavior of black holes with quantum mechanics, particularly with regard to the flow of time. According to general relativity, time slows down as you approach the event horizon of a black hole, the point of no return beyond which nothing can escape. For an outside observer, time appears to stop at the event horizon. This raises paradoxes about what happens to information that falls into a black hole. In quantum mechanics, information cannot be destroyed, but in classical general relativity, any information about the matter that falls into a black hole seems to be lost forever. This paradox is known as the information paradox, and it has led to major debates in the physics community. One potential solution to the information paradox comes from the idea of black hole complementarity, which suggests that information is both reflected at the event horizon and passes through it, depending on the observer's point of view. Another idea is the holographic principle, which posits that all the information contained within a black hole is actually encoded on its surface, the event horizon, rather than inside the black hole itself. This idea has profound implications for our understanding of space, time, and the fundamental nature of reality. If the holographic principle is correct, it could suggest that the entire universe is a kind of hologram, with the information we perceive as three-dimensional reality being encoded on a two-dimensional surface. The concept of a holographic universe is one of the most radical and intriguing ideas in modern theoretical physics. It emerged from attempts to reconcile quantum mechanics with general relativity and the study of black hole thermodynamics. If the universe is indeed holographic, it could mean that what we experience as physical reality is actually a projection of information encoded on the boundary of the universe. This challenges our everyday intuitions about space, time, and reality, and raises profound questions about the nature of existence. The mysteries of the universe extend not only to its large-scale structure, but also to the smallest scales of existence. The world of quantum mechanics is filled with bizarre and counterintuitive phenomena that defy our classical understanding of reality. In the quantum realm, particles behave like waves, existing in a superposition of states until observed. This leads to strange phenomena such as quantum tunneling, where particles can pass through barriers that should be impenetrable, and quantum entanglement, where particles become linked in such a way that the state of one instantly affects the state of the other, no matter how far apart they are. These quantum phenomena challenge our classical notions of locality and causality, forcing us to reconsider our understanding of space and time. Quantum tunneling, for instance, suggests that particles can move through space in ways that defy our normal understanding of trajectories. In the everyday world, if you throw a ball at a wall, it either bounces back or is stopped by the wall. But at the quantum level, particles can sometimes pass right through the barrier as if it wasn't there. This phenomenon is crucial to many processes in the universe, from the fusion reactions that power the sun to the operation of electronic devices like transistors. Quantum entanglement, perhaps the most famous and perplexing quantum phenomenon, further challenges our ideas about how the universe works. When two particles are entangled, the state of one particle is instantaneously correlated with the state of the other, no matter how far apart they are. If you measure one particle and find it in a particular state, the other particle will immediately be found in the corresponding state, as if the two particles are communicating faster than the speed of light. This spooky action at a distance, as Einstein called it, seems to violate the principle of locality, which states that objects should only be able to influence each other through signals that travel through space over time. One interpretation of quantum entanglement is that the particles are not actually separated in the way we think they are. Instead, they are part of a single, unified quantum system, and their entanglement reflects the deep interconnectedness of the quantum world. Another interpretation comes from the many worlds theory of quantum mechanics, which posits that every quantum event spawns new branches of reality, and that in one branch, the first particle is in one state, while in another branch, the second particle is in the corresponding state. These interpretations challenge our classical notions of a singular, objective reality and suggest that the universe may be far stranger and more complex than we can easily comprehend. Quantum mechanics also raises profound questions about the role of the observer in shaping reality. In the famous double-slit experiment, particles such as electrons exhibit wave-like behavior when not observed, creating an interference pattern as if they pass through both slits simultaneously. However, when the particles are observed, they behave like classical particles, passing through one slit or the other. This suggests that the act of observation collapses the quantum wave function, forcing the particle into a definite state. This observer effect has led some physicists and philosophers to speculate that consciousness itself may play a fundamental role in the structure of the universe, though this idea remains highly controversial. The mystery of quantum mechanics is not limited to its bizarre phenomena. It also extends to the problem of unifying quantum theory with general relativity. Quantum mechanics describes the behavior of particles at the smallest scales, while general relativity describes the behavior of spacetime at the largest scales. But these two theories are fundamentally incompatible. General relativity is a classical theory that treats spacetime as a smooth, continuous fabric, while quantum mechanics describes reality in terms of discrete, probabilistic events. The search for a theory of quantum gravity, which would unify these two frameworks, is one of the greatest unsolved problems in physics. One candidate for a theory of quantum gravity is string theory, which posits that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. These strings can vibrate in different ways, giving rise to the various particles and forces we observe. String theory also suggests the existence of extra dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. In some versions of string theory, these extra dimensions are compactified, meaning they are curled up so tightly that they are imperceptible to us. In others, the universe may have large, additional dimensions that we are unable to detect because we are confined to a 3-dimensional brain within a higher dimensional space. The idea of extra dimensions is not just a theoretical curiosity. It has deep implications for our understanding of the universe. If extra dimensions exist, they could help explain some of the most puzzling features of the cosmos, such as the weakness of gravity compared to the other fundamental forces. Gravity could be leaking into these extra dimensions, which would explain why it appears so much weaker than, say, electromagnetism. Extra dimensions might also play a role in the formation of black holes, the behavior of dark matter, and the overall structure of the universe. In addition to string theory, another approach to quantum gravity is loop quantum gravity, which suggests that spacetime itself is quantized, meaning it has a discrete, granular structure at the smallest scales. In this view, spacetime is not a smooth continuum, but is composed of tiny loops of quantum geometry. This theory offers a possible explanation for the behavior of black holes, suggesting that the singularities at their centers may not be infinite points but rather regions where spacetime is densely packed with quantum loops. However, both string theory and loop quantum gravity remain speculative, and neither has been experimentally confirmed. The mystery of quantum gravity is closely tied to the mystery of the Big Bang. According to the standard cosmological model, the universe began as an incredibly hot, dense point, often referred to as a singularity, and has been expanding ever since. But the laws of physics as we currently understand them break down at the moment of the Big Bang, making it difficult to describe the true nature of the universe's origin. A theory of quantum gravity might provide a more complete picture of the Big Bang, showing how the universe emerged from a quantum state of spacetime. Some theories suggest that the Big Bang may not have been the beginning of everything but rather a transition from a previous state of the universe. For example, in the cyclic model, the universe undergoes a series of expansions and contractions, with each Big Bang marking the beginning of a new cycle. Other models propose that the Big Bang was a quantum fluctuation in a pre-existing multiverse of possible universes. In this view, our universe is just one of many, each with its own set of physical laws and conditions. This idea raises the possibility that the constants of nature, such as the strength of gravity or the charge of the electron, may be different in other universes, leading to wildly different kinds of realities. The concept of the multiverse is one of the most speculative yet fascinating ideas in modern cosmology. If the multiverse exists, it could help explain why our universe appears so finely tuned for the existence of life. In a vast multiverse of many possible universes, it is not surprising that at least one would have the right conditions for life to arise. But the multiverse also raises profound questions about the nature of reality and the limits of scientific knowledge. If other universes exist, they may be forever beyond our reach, making them impossible to observe or study directly. Does this mean that the multiverse is purely a philosophical construct, or could there be ways to test its existence? The mystery of the multiverse ties into the deeper question of why there is something rather than nothing. Why does the universe exist at all? Why is there a universe with matter, energy, and physical laws, rather than a void of nothingness? This question has puzzled philosophers and scientists for centuries and remains one of the most profound mysteries of existence. Some physicists propose that the universe could have arisen spontaneously from a quantum vacuum, a state of nothing that is not truly empty but filled with fluctuating quantum fields. According to this view, the laws of quantum mechanics allow for the spontaneous creation of universes from nothing, much like how particles can spontaneously pop into existence in the quantum vacuum. But this explanation still leaves many questions unanswered. If the universe arose from a quantum vacuum, what set the conditions for the quantum vacuum to exist in the first place? And why do the laws of quantum mechanics permit the existence of something rather than nothing? These questions touch on the deepest mysteries of cosmology, philosophy, and metaphysics, and they may ultimately lie beyond the reach of science. As we continue to explore the mysteries of the universe, we are constantly reminded of how much we still don't know. Every new discovery seems to raise more questions than it answers, revealing deeper layers of complexity and wonder. Whether we are studying the behavior of subatomic particles, the formation of galaxies, or the nature of time itself, we are confronted with the profound realization that the universe is far stranger and more mysterious than we ever imagined. And yet, it is this very mystery that drives us to keep searching, to keep asking questions, and to keep pushing the boundaries of human knowledge. The search for answers to the mysteries of the universe is a journey that has spanned millennia. Humanity's fascination with the cosmos can be traced back to ancient civilizations, where early stargazers sought to understand the heavens through myths, legends, and rudimentary observations. These ancient observers could never have imagined the complexity of the universe that modern science has uncovered. Yet, even with all the technological advancements and sophisticated theories at our disposal today, we are still humbled by how much remains unexplained. One of the most profound mysteries that continues to baffle scientists is the nature of dark matter and dark energy. These two components together make up about 95% of the total mass energy content of the universe, yet we have almost no direct knowledge of what they are. Visible matter, the stuff that makes up stars, planets, and galaxies, accounts for only about 5% of the universe. The rest is hidden in the form of dark matter and dark energy, which we can only infer from their gravitational effects on the visible universe. Dark matter was first hypothesized in the 1930s when astronomers observed that galaxies were rotating faster than expected based on the amount of visible matter they contained. According to the laws of gravity, galaxies should have torn themselves apart long ago if only visible matter were present to hold them together. The gravitational pull of some unseen mass, dark matter, seems to be providing the extra force needed to keep galaxies intact. But what is dark matter? No one knows for sure. It does not emit, absorb, or reflect light, making it invisible to telescopes. It could be composed of some unknown type of particle, or it might represent a flaw in our understanding of gravity. There have been numerous attempts to detect dark matter directly through experiments designed to catch the elusive particles as they pass through Earth. But so far, these efforts have come up empty. Some theories suggest that dark matter might consist of weakly interacting massive particles, WIMPs, while others propose that it could be made of axions, neutrinos, or even more exotic particles like sterile neutrinos or supersymmetric particles. Until we can directly observe dark matter or its effects more clearly, it remains one of the most significant unsolved mysteries in modern physics. If dark matter is mysterious, dark energy is even more perplexing. In the late 1990s, astronomers made a startling discovery. The expansion of the universe is not slowing down, as had been expected, but is actually accelerating. This acceleration is thought to be driven by a mysterious form of energy that permeates all of space, dubbed dark energy. While we can measure the effects of dark energy on the universe's expansion, we have no idea what it actually is. Some theories suggest that dark energy could be a property of space itself, a sort of cosmological constant that Einstein once included in his equations of general relativity, only to later dismiss as his biggest blunder. Other theories propose that dark energy could be related to the quantum vacuum, with empty space having a small amount of intrinsic energy that drives the universe's expansion. There are even more speculative ideas that suggest dark energy might be a sign that our universe is part of a multiverse, with different regions of the multiverse having different values of dark energy. The discovery of dark energy has fundamentally changed our understanding of the fate of the universe. In the past, scientists debated whether the universe would end in a big crunch, where gravity would eventually halt the expansion and cause everything to collapse back into a singularity, or in a heat death, where the universe would keep expanding but gradually cool down and run out of usable energy. Now, with the discovery of dark energy, it seems more likely that the universe will continue expanding forever, with galaxies drifting farther apart until they are no longer visible to each other, leaving a cold, dark, and empty universe in the distant future. But the mysteries of the universe don't end with dark matter and dark energy. There are also the questions of how and why the fundamental constants of nature are so finely tuned for the existence of life. The strength of the electromagnetic force, the mass of the proton, the rate of expansion of the universe. These and many other constants all have values that, if they were just slightly different, would make life as we know it impossible. If the force of gravity were slightly stronger or weaker, stars wouldn't be able to form, or they would burn out too quickly. If the charge of the electron were different, atoms wouldn't hold together. This fine-tuning has led some to propose the anthropic principle, which suggests that the universe appears fine-tuned for life because, if it weren't, we wouldn't be here to observe it. But the anthropic principle raises more questions than it answers. Why should the universe be fine-tuned for life in the first place? Is it a cosmic coincidence? Or is there some deeper reason? One possible explanation is the multiverse theory, which suggests that our universe is just one of many, each with its own set of physical laws and constants. In this view, it's not surprising that at least one universe would have the right conditions for life, just as it's not surprising that at least one planet, among the trillions in the cosmos, would have the right conditions for life. But the multiverse theory is difficult to test, and some scientists argue that it's more of a philosophical idea than a scientific hypothesis. Another possibility is that the fine-tuning of the universe is the result of some deeper, undiscovered physical laws. Perhaps the constants of nature aren't arbitrary at all, but are determined by some as yet unknown principles of physics. Or maybe the universe was designed, either by a deity or by some other form of intelligence, to support life. This idea, known as intelligent design, is controversial and is generally not considered a scientific explanation, as it relies on supernatural intervention rather than testable hypotheses. In addition to the fine-tuning problem, there is also the mystery of the arrow of time. Why does time seem to flow in one direction, from the past to the future, when the laws of physics are time-symmetric? In most physical processes, there's no distinction between past and future. If you ran the clock backward, the process would look just as valid as it does moving forward. But in our everyday experience, time clearly has a direction. We remember the past but not the future, and events unfold in a sequence from cause to effect. The arrow of time is closely related to the second law of thermodynamics, which states that the total entropy, or disorder, of a closed system always increases over time. This increase in entropy gives time its apparent direction, but the deeper question of why the universe started in such a low entropy state, one that allows for the increase of entropy over time, remains unanswered. Some scientists propose that the arrow of time is linked to the expansion of the universe. As the universe expands, it creates more room for entropy to increase, giving time its forward direction. Others suggest that the arrow of time might be an illusion, a result of our limited perspective as beings embedded in time. Perhaps at a deeper, more fundamental level, time is symmetrical, and what we perceive as the flow of time is merely an emergent property of the way we process information. The mystery of time also touches on the question of the nature of space and time themselves. In Einstein's theory of general relativity, space and time are not fixed, immutable backgrounds against which events play out, but are dynamic, flexible entities that are shaped by the presence of matter and energy. In this view, space and time are intertwined into a four-dimensional fabric known as spacetime, and the curvature of spacetime is what we perceive as gravity. This idea has been confirmed by numerous experiments, such as the bending of light around massive objects and the precise measurements of time dilation in satellites orbiting Earth. However, the nature of spacetime remains deeply mysterious. Is spacetime a continuous fabric, Or is it made up of discrete, quantized units at the smallest scales? Theories of quantum gravity, such as loop quantum gravity, suggest that spacetime might be composed of tiny, indivisible loops or quanta of geometry, much like how matter is made up of atoms. If this is the case, it would mean that space and time are not smooth, but have a granular structure at the Planck scale, which is many orders of magnitude smaller than the size of an atom. This granular nature of spacetime, if proven, would revolutionize our understanding of the universe. It would imply that space and time themselves are emergent properties, not fundamental elements of reality. Just as the temperature of an object is an emergent property of the motion of its atoms, spacetime might emerge from more basic, underlying principles that we have yet to fully comprehend. The search for a theory of quantum gravity, one that unites the general theory of relativity with quantum mechanics, has been one of the greatest challenges in modern physics. String theory, another leading candidate for quantum gravity, proposes that the fundamental building blocks of reality are not point particles but tiny, vibrating strings, whose vibrations give rise to the different particles and forces we observe. String theory also introduces the idea of extra dimensions of space beyond the familiar three. According to the theory, there may be as many as 10 or 11 dimensions, but these extra dimensions are curled up so tightly that they are invisible to us. This idea, while mathematically elegant, remains speculative, as we currently have no way of testing the existence of these extra dimensions. However, the potential implications of string theory are mind-boggling. If it is correct, it could provide a unified description of all the forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, in a single framework. But even if we could develop a complete theory of quantum gravity, it might not answer all of our questions. One of the deepest mysteries of the universe is the question of why there is something rather than nothing. The very existence of the universe, and of everything within it, poses a profound puzzle. The laws of physics, as we understand them, do not seem to forbid the existence of nothingness, yet here we are, in a universe full of matter, energy, space, and time. Some physicists have suggested that the universe could have emerged from a quantum fluctuation in the vacuum, a process allowed by the uncertainty principle of quantum mechanics. In this view, nothingness is not truly empty but is a seething sea of virtual particles and energy that occasionally gives rise to entire universes. This idea, known as the quantum creation hypothesis, offers a possible explanation for the origin of the universe, but it raises new questions about the nature of the vacuum and why the laws of physics are what they are. Another mystery related to the origins of the universe is the nature of the Big Bang itself. According to the Standard Model of Cosmology, the universe began about 13.8 billion years ago in a state of extremely high temperature and density, and has been expanding ever since. But what caused the Big Bang? What, if anything, existed before it? And is the Big Bang truly the beginning of everything, or was it just a transition point in a larger cosmic cycle? Some theories suggest that the Big Bang might not have been the absolute beginning of the universe, but rather the result of a previous universe collapsing in a big crunch, and then rebounding in a new Big Bang. This idea, known as the cyclic universe model, proposes that the universe goes through endless cycles of expansion and contraction, with each cycle beginning with a Big Bang and ending with a big crunch. In this view, the universe has no true beginning or end, but is eternal, cycling through phases of birth and rebirth. Another idea is that our universe is part of a multiverse, and the Big Bang was the result of a collision or interaction between different bubble universes within the multiverse. In this scenario, the multiverse contains an infinite or near-infinite number of universes, each with its own physical laws and constants. Our universe just happens to be one of the bubbles that was able to give rise to life. The concept of the multiverse is one of the most speculative ideas in modern physics, but it has gained traction as a possible solution to the fine-tuning problem and other cosmological puzzles. However, the multiverse theory is difficult to test or falsify, as the other universes, if they exist, are thought to be beyond our observational reach. Nonetheless, it opens up the tantalizing possibility that there are countless other universes out there, each with its own mysteries and unknowns. Beyond the mysteries of the cosmos, there are also profound questions about the nature of life and consciousness. How did life emerge from the primordial soup of chemicals on Earth? Is life a rare and unique phenomenon, or is it common throughout the universe? The discovery of exoplanets, planets orbiting other stars, has shown that there are likely billions of potentially habitable planets in our galaxy alone, raising the possibility that life could exist elsewhere in the universe. But despite decades of searching, we have yet to find any definitive evidence of extraterrestrial life. The question of life's origins is deeply tied to the question of how the universe itself is structured. Some scientists have proposed the idea of a biocentric universe, where the fundamental constants and laws of physics are fine-tuned not just for the existence of matter and energy, but for the emergence of life and consciousness. In this view, life is not just a byproduct of the universe's evolution, but an essential part of its fabric. Others argue that life is a rare accident, the result of a fortunate set of circumstances that came together on Earth but are unlikely to be repeated elsewhere. The mystery of consciousness is even more perplexing. How do the physical processes in our brains give rise to subjective experience, self-awareness, and the sense of being? This hard problem of consciousness has baffled philosophers and scientists for centuries, and there is still no consensus on how to solve it. Some researchers propose that consciousness is an emergent property of complex neural networks, while others suggest that it might be a fundamental aspect of reality, much like space and time. One radical idea, known as panpsychism, posits that consciousness is a basic property of all matter, not just living organisms. In this view, even inanimate objects, like rocks and stars, possess some form of rudimentary consciousness. While this idea is controversial and difficult to test, it challenges our traditional understanding of the relationship between mind and matter and opens up new possibilities for how consciousness might be understood in the context of the universe. As we contemplate these mysteries, we are reminded of the vastness of the unknown. The universe is not just a collection of stars, planets, and galaxies. It is a deep and intricate web of mysteries that challenge our most basic assumptions about reality. From the nature of dark matter and dark energy to the origins of life and consciousness, the universe is filled with questions that may take centuries, if not millennia, to fully answer. Perhaps the greatest mystery of all is whether we will ever reach a complete understanding of the universe. Will there come a time when we have unraveled all the secrets of the cosmos? Or are there some mysteries that are simply beyond our grasp? As we continue to explore the universe, we must remain open to the possibility that some of its mysteries may never be fully solved. But it is this very sense of wonder and curiosity that drives us to keep searching, to keep asking questions, and to keep pushing the boundaries of our knowledge. The mysteries of the universe, far from being static, evolve as our understanding deepens. Each new discovery or breakthrough leads to more questions, suggesting that the universe may be infinite not just in size but in complexity. As we seek to unlock the secrets of the cosmos, we encounter concepts and phenomena that push the limits of human comprehension. One of the most profound mysteries concerns the ultimate fate of the universe. While we understand that the universe is expanding, the long-term consequences of this expansion are still unknown. The dominant theory suggests that the universe will continue expanding indefinitely in a process known as the Big Freeze, or heat death. As galaxies move farther apart and stars burn out, the universe will grow colder and darker until it reaches a state of maximum entropy, where all energy is evenly distributed and no further thermodynamic processes can occur. In this bleak future, the universe would be a cold, empty, and lifeless place. However, other theories offer different possibilities. Some propose that the universe's expansion could eventually reverse, leading to a big crunch, where the universe collapses back in on itself, potentially giving rise to a new Big Bang and a new cycle of cosmic evolution. This cyclic model of the universe suggests an eternal process of creation, destruction, and rebirth. Another intriguing possibility is the Big Rip scenario, where the expansion of the universe accelerates to the point that it overcomes all forces, including gravity. In this case, not only would galaxies drift apart, but stars, planets, and even atoms would be torn apart by the relentless expansion of spacetime. The universe would end in a violent disintegration, with all matter and energy scattered into an unrecognizable state. These various end-of-the-universe scenarios are driven by our understanding of dark energy, the mysterious force responsible for the accelerating expansion of the universe. Dark energy remains one of the greatest enigmas in modern cosmology. While it constitutes about 68% of the universe's total energy content, we have no direct way of detecting it or understanding its nature. Is dark energy a constant, unchanging property of spacetime, or could it evolve over time? If it changes, how might that affect the future of the universe? These questions remain unanswered, and the true nature of dark energy continues to elude us. Beyond the fate of the universe, we are also confronted with the question of whether our understanding of physics is complete. The standard model of particle physics, while incredibly successful in explaining the behavior of fundamental particles, is not without its gaps. For instance, it cannot account for the masses of neutrinos, the nature of dark matter, or the force of gravity. Physicists are searching for a more comprehensive theory that unifies the forces of nature and explains phenomena that the standard model cannot. One promising avenue is the search for supersymmetry, a theoretical framework that extends the standard model by proposing a symmetry between particles known as fermions, which make up matter, and bosons, which carry forces. Supersymmetry predicts the existence of a whole new set of particles, many of which could help explain dark matter. However, despite extensive searches, no direct evidence for supersymmetry has yet been found, and its status remains uncertain. In addition to these fundamental mysteries, we are also exploring the possibility that the laws of physics themselves may vary across space and time. Some theories suggest that the constants of nature, such as the speed of light or the strength of the electromagnetic force, might not be fixed but could change over cosmic distances or over long periods of time. If this is true, it would have profound implications for our understanding of the universe, as it would suggest that the laws of physics are not universal, but are shaped by the particular conditions of different regions of the cosmos. The question of whether we live in a universe governed by constant, immutable laws or one where the rules are flexible and subject to change is a fundamental one. It strikes at the heart of our efforts to understand the universe, as it challenges the very notion of a consistent, predictable reality. Another area of exploration is the nature of time itself. Time, as we experience it, appears to flow in one direction, from past to future. This arrow of time is closely tied to the concept of entropy, which always increases in a closed system. However, the laws of physics are mostly time-symmetric, meaning they work equally well if time is reversed. Why, then, does time seem to flow in only one direction? Some physicists suggest that the arrow of time is a consequence of the universe's initial conditions, specifically, the low-entropy state of the universe at the time of the Big Bang. As the universe expands and entropy increases, the arrow of time emerges naturally. Others speculate that time might be an emergent property, not a fundamental aspect of reality, and that on the smallest scales, time may behave very differently from how we perceive it. There are also theories that propose the existence of multiple timelines or parallel universes, each with its own distinct version of events. In this view, every possible outcome of a quantum event spawns a new timeline, creating an ever-branching tree of parallel realities. This idea, known as the many worlds interpretation of quantum mechanics, offers a way to resolve some of the paradoxes of quantum theory, such as the apparent randomness of quantum events. If the many worlds interpretation is correct, it means that there are countless parallel universes, each representing a different version of reality. In some universes, events may have played out very similarly to our own, while in others, they may have diverged dramatically. The implications of this idea are staggering, as it suggests that every possible version of reality exists somewhere in the multiverse, including versions of ourselves living out different lives based on the choices we did or did not make. While the many worlds interpretation remains controversial, it highlights the deep and often bewildering nature of quantum mechanics. At the smallest scales, the universe behaves in ways that defy our everyday intuition. Particles can exist in multiple states simultaneously, a phenomenon known as superposition, and they can be entangled with one another, meaning that the state of one particle is instantaneously linked to the state of another, even if they are separated by vast distances. This phenomenon, known as quantum entanglement, was once described by Einstein as spooky action at a distance, and it challenges our understanding of causality and locality. Quantum mechanics also raises questions about the role of the observer in shaping reality. According to the Copenhagen interpretation, the act of measurement collapses a quantum system from a superposition of states into a single definite state. In this view, reality is not fully determined until it is observed. This idea has led to much philosophical debate about the nature of reality and the role of consciousness in shaping the universe. Is the universe fundamentally objective, existing independently of observers, or does the act of observation play a crucial role in bringing reality into being? This question touches on the age-old debate between realism and idealism, and it has profound implications for our understanding of the nature of the cosmos. As we delve deeper into these mysteries, we are reminded that the universe is not just a collection of matter and energy. It is a vast, interconnected web of possibilities, governed by rules that we are only beginning to understand. The more we learn, the more we realize how much we have yet to discover. Each new discovery opens up new realms of inquiry, and each new question leads us deeper into the unknown. In the end, the mysteries of the universe may never be fully solved. But it is this very sense of wonder and curiosity that drives us to keep exploring, to keep asking questions, and to keep seeking answers, no matter how elusive they may be. The mysteries of the universe also extend into realms that challenge the very fabric of reality itself. One such profound mystery is the nature of consciousness and its place in the cosmos. Consciousness, the subjective experience of awareness and thought, remains one of the greatest enigmas in both science and philosophy. While the brain's role in producing consciousness is well documented, the underlying mechanism that gives rise to subjective experience, what philosophers call the hard problem of consciousness, is still unknown. What is the relationship between the physical processes of the brain and the feeling of being a conscious, thinking individual? Is consciousness merely an emergent property of complex neural activity, or could it be a fundamental feature of the universe itself? Some theories propose that consciousness could be linked to quantum processes in the brain, suggesting that the strange, non-deterministic behavior of quantum particles might play a role in the formation of conscious thought. This idea, while highly speculative, opens up the possibility that consciousness is not an isolated phenomenon restricted to biological life but could instead be woven into the very fabric of reality. If this is the case, it raises fascinating questions about whether other entities, artificial intelligence, advanced alien civilizations, or even the universe itself, could possess some form of consciousness. There is also the notion that consciousness might be fundamental, as suggested by certain interpretations of panpsychism. Panpsychism posits that consciousness is not something that arises from matter, but rather that all matter, in some sense, has a form of consciousness. In this view, the universe is not made up solely of inert, unconscious particles, but is imbued with some form of mental or experiential quality at every level of existence. If true, this would radically alter our understanding of the universe, suggesting that consciousness permeates all of reality, and that our own subjective experience is but a small part of a much larger cosmic mind. These ideas lead to the tantalizing possibility that the universe itself could be conscious, or at least that it could have some form of awareness. This concept, sometimes referred to as the conscious universe hypothesis, challenges the traditional, mechanistic view of the cosmos as a vast, indifferent expanse of matter and energy. Instead, it presents a universe that is not only alive with physical processes but also with mental or conscious phenomena. Whether or not the universe is conscious, the question of life beyond Earth adds another layer of mystery to our understanding of the cosmos. For decades, scientists have searched for signs of extraterrestrial life, both within our solar system and beyond. The discovery of microbial life on Mars, Europa, or other celestial bodies would revolutionize our understanding of biology and the conditions necessary for life. But the ultimate question, are we alone in the universe, remains unanswered. The search for extraterrestrial intelligence, SETI, has scanned the skies for decades, hoping to detect radio signals or other signs of advanced civilizations. So far, this search has yielded no definitive results, leading to the formulation of the Fermi paradox. The Fermi paradox asks why, given the vast number of stars and planets in the universe, we have not yet encountered any evidence of intelligent extraterrestrial life. There are many potential explanations for this paradox, ranging from the possibility that advanced civilizations are rare or short-lived, to the idea that they may be deliberately avoiding contact with us. One of the more unsettling solutions to the Fermi paradox is the concept of the Great Filter, which suggests that there is some barrier or obstacle that prevents civilizations from reaching the point of interstellar communication or exploration. This filter could occur at any stage in a civilization's development. Perhaps the emergence of life itself is exceedingly rare, or maybe advanced civilizations tend to self-destruct before they can expand into the galaxy. The idea of the Great Filter raises existential questions about humanity's future. Have we already passed this filter, or does it still lie ahead of us? In the absence of direct evidence of extraterrestrial civilizations, some scientists and philosophers have speculated that we might be living in a simulation. The simulation hypothesis suggests that our reality is an artificial construct, created by a more advanced civilization, much like a highly sophisticated computer simulation. Proponents of this theory argue that if it is possible for advanced civilizations to create simulations of reality, and if these simulations are indistinguishable from the real world, then it is statistically likely that we are living in one of many such simulations. The simulation hypothesis challenges our basic assumptions about reality and raises profound questions about free will, the nature of existence, and the ultimate purpose of life. If we are living in a simulation, are we subject to the whims of the beings or entities running the simulation? Is there an escape from the simulation, or are we forever trapped within it? And what is the purpose of such a simulation? Are we part of a grand experiment, or is our reality simply a form of entertainment for higher beings? As we contemplate these questions, we must also consider the possibility that our universe is not the only one. The concept of the multiverse suggests that there are many, perhaps an infinite number of universes, each with its own unique set of physical laws and constants. In some of these universes, the conditions might be radically different from our own, with alternate forms of matter, energy, and even life. In others, the laws of physics might be so different that they defy human comprehension altogether. The idea of the multiverse arises from several different branches of physics, including string theory and cosmology. According to the theory of cosmic inflation, the rapid expansion of the universe in the moments after the Big Bang could have created pocket universes, each with its own distinct properties. String theory, meanwhile, suggests that our universe might be one of many that exist within a higher dimensional space, like bubbles floating in an infinite ocean of possibilities. If the multiverse exists, it raises profound questions about the nature of reality and our place within it. Are there other versions of ourselves living out different lives in parallel universes? Could we ever travel between universes? Or are we forever confined to our own cosmic bubble? And what does the existence of the multiverse mean for our understanding of fundamental concepts like time, space, and causality? The possibility of the multiverse also touches on the question of fine-tuning in the universe. Many of the fundamental constants of nature, such as the strength of gravity or the charge of the electron, appear to be finely tuned to allow for the existence of life. If these constants were even slightly different, life as we know it would not be possible. Some scientists argue that this fine-tuning suggests the universe was designed with life in mind, while others propose that the multiverse offers a more natural explanation. In a multiverse with infinite variations, it is inevitable that at least one universe would have the right conditions for life to emerge. Whether or not the multiverse exists, it highlights the vastness and complexity of the cosmos, and the limits of our current understanding. As we push the boundaries of human knowledge, we are constantly reminded of how much we have yet to learn. The universe is a place of infinite wonder, filled with mysteries that challenge our intellect and inspire our imagination. Even as we grapple with these grand cosmic questions, we must not lose sight of the fact that the universe is also a place of extraordinary beauty. From the majestic spiral arms of distant galaxies to the delicate dance of subatomic particles, the cosmos is filled with patterns and structures that are both awe-inspiring and deeply mysterious. The more we learn about the universe, the more we come to appreciate its intricacy and elegance. As we look to the future, the mysteries of the universe will continue to captivate and inspire us. Advances in technology and scientific understanding will undoubtedly bring new discoveries and new questions, expanding our knowledge while also revealing the limitations of our current frameworks. In this endless quest for understanding, we are driven by the same curiosity that has fueled human exploration for millennia, a desire to know who we are, where we come from, and what lies beyond the horizon. Ultimately, the mysteries of the universe remind us of the profound connection between science, philosophy, and the human experience. Our search for answers is not just a quest for knowledge, it is a search for meaning, a way of understanding our place in the grand tapestry of existence. Whether or not we ever fully solve these mysteries, the journey itself is a testament to the power of human curiosity and the boundless potential of the human mind. As we delve deeper into the universe's mysteries, the relationship between time and space remains one of the most perplexing and intriguing concepts. Traditionally, we perceive time as a linear progression, past, present, and future, while space is seen as the three-dimensional expanse in which all objects exist. However, modern physics has challenged these intuitive notions, revealing that time and space are interwoven in a way that fundamentally alters our understanding of reality. Einstein's theory of relativity revolutionized our conception of time and space. According to relativity, time is not a fixed backdrop against which events occur but rather a flexible dimension that can be affected by gravity and velocity. The famous thought experiment of twin paradox illustrates this principle. If one twin travels at a high velocity through space while the other remains on Earth, the traveling twin will age more slowly than the twin who stays behind. This counterintuitive result arises from the curvature of spacetime, a four-dimensional continuum in which the effects of gravity warp the fabric of reality. Moreover, the concept of time itself is far from simple. Is time a fundamental aspect of the universe, or is it an emergent property arising from more basic elements? Some physicists speculate that time may not exist at all in the absence of observers. This notion aligns with interpretations of quantum mechanics, which suggests that particles do not have definite properties until they are observed. If time is intrinsically linked to consciousness, what implications does that hold for our understanding of reality? These philosophical implications extend into practical realms as well, such as the study of black holes. Black holes represent one of the universe's most enigmatic features, regions where the gravitational pull is so strong that nothing, not even light, can escape. At the center of a black hole lies a singularity, a point where density becomes infinite, and the laws of physics, as we know them, break down. This creates a paradoxical situation. While we can observe the effects of black holes on surrounding matter, their interiors remain hidden from our understanding. Furthermore, the event horizon of a black hole poses questions about information and reality itself. According to the laws of physics, information cannot be destroyed. However, it appears that anything falling into a black hole is lost to the outside universe. This dilemma leads to the black hole information paradox, a topic of heated debate among physicists. Some theories propose that information is preserved in some form, perhaps as a holographic projection on the event horizon or through quantum entanglement, hinting at a deeper, still unknown connection between quantum mechanics and gravity. The quest to understand black holes also intersects with the pursuit of a theory of quantum gravity, a framework that seeks to reconcile general relativity, which governs large-scale cosmic phenomena, with quantum mechanics, which describes the behavior of subatomic particles. Finding a unifying theory that can elegantly describe both realms remains one of the holy grails of modern physics. Approaches such as string theory, loop quantum gravity, and others seek to bridge this divide, but a comprehensive solution remains elusive. The universe's expansion adds yet another layer of complexity to our understanding of time and space. Observations reveal that the universe has been expanding since the Big Bang, with galaxies moving away from each other in a phenomenon known as redshift. Surprisingly, recent discoveries indicate that this expansion is accelerating, driven by a mysterious force dubbed Dark energy. Dark energy, which is believed to make up about 68% of the universe, remains one of the biggest puzzles in cosmology. What is its nature? Why does it cause the universe to expand at an ever-increasing rate? Addressing these questions could have profound implications for our understanding of the universe's fate. The fate of the universe itself is another captivating mystery. Current theories suggest several possible scenarios for the long-term future of the cosmos. In one scenario, known as the Big Freeze, the universe continues to expand indefinitely, leading to a state where galaxies drift apart and stars burn out, resulting in a dark, cold cosmos devoid of activity. Another possibility is the Big Crunch, where the expansion eventually reverses, leading to a collapse of the universe back into a singularity, potentially followed by another Big Bang. Finally, there is the speculative Big Rip, where the expansion accelerates to such an extent that it tears apart galaxies, stars, and even atomic particles. The eventual fate of the universe is tightly linked to the nature of dark energy and the overall geometry of space. Current observations suggest that the universe is flat, meaning it will expand forever, but there remains uncertainty. Understanding the fundamental properties of dark energy and its role in cosmic evolution is crucial to piecing together this grand puzzle. While these scientific inquiries push the boundaries of human knowledge, they also inspire a sense of wonder and curiosity about our place in the cosmos. The mysteries of the universe remind us of our shared human experience, our thirst for understanding and our desire to connect with something larger than ourselves. This quest for knowledge has driven humanity's greatest achievements, from the exploration of our own planet to the voyages into the depths of space. As we continue to unravel the mysteries of the universe, we must also consider the role of technology in our exploration. The development of advanced telescopes, space probes, and particle accelerators has opened new frontiers in our quest for understanding. The Hubble Space Telescope has captured breathtaking images of distant galaxies, while the upcoming James Webb Space Telescope promises to delve even deeper into the cosmos, unveiling the secrets of star formation and the atmospheres of exoplanets. In addition to observational advancements, the field of artificial intelligence is transforming how we analyze and interpret vast amounts of astronomical data. Machine learning algorithms are increasingly used to identify patterns, classify celestial objects, and make predictions about the universe's behavior. As technology continues to evolve, so too will our ability to probe the mysteries of the cosmos, potentially leading to groundbreaking discoveries that reshape our understanding of reality. The intersection of science and philosophy is another important aspect of our exploration of the universe's mysteries. Questions about the nature of reality, the existence of consciousness, and the implications of our discoveries extend beyond the confines of empirical research. Philosophers grapple with the ethical implications of advanced technologies, the meaning of existence in a vast and indifferent universe, and the potential consequences of contact with extraterrestrial life. The dialogue between science and philosophy enriches our understanding of the universe and helps us navigate the profound implications of our findings. As we stand on the brink of new discoveries and insights, we are reminded that the journey is just as important as the destination. The mysteries of the universe invite us to wonder, to explore, and to question. They compel us to seek knowledge not only for its own sake but also for the sake of understanding ourselves and our place in the grand tapestry of existence. In the end, the universe is not merely a collection of stars, planets, and galaxies. It is a dynamic, ever-evolving system that reflects our aspirations, fears, and dreams. The quest to uncover its mysteries is a testament to the resilience of the human spirit, a reminder that, despite our limitations, we are driven by an innate desire to explore the unknown. As we ponder the mysteries of the universe, we must also recognize the beauty and interconnectedness of all things. From the smallest subatomic particles to the vast expanse of the cosmos, everything is part of a greater whole. Each discovery we make adds a brushstroke to the grand canvas of existence, illuminating our understanding and enriching our appreciation for the world around us. Ultimately, the mysteries of the universe invite us to embrace uncertainty, to revel in the unknown, and to continue our journey of exploration and discovery. They challenge us to question our assumptions, to expand our horizons, and to engage with the wonders of reality in all their complexity. As we venture forth into the cosmos, we do so with the knowledge that the mysteries may never be fully unraveled, but the pursuit of understanding is, in itself, a profound and meaningful endeavor. As we continue to explore the vast expanses of the universe, one cannot ignore the captivating concept of multiverses. The idea that our universe may be just one of many universes has gained traction in both scientific and philosophical circles. This hypothesis challenges the notion that our universe is unique, suggesting instead that there could be countless other universes, each with its own set of physical laws and constants. Some theories propose that these universes exist in parallel, coexisting within a larger multiverse framework, while others suggest that they could emerge from different initial conditions during cosmic inflation. The concept of a multiverse raises profound questions about the nature of reality and existence. If there are indeed multiple universes, what does that mean for our understanding of probability and chance? In a multiverse scenario, every possible outcome could exist in some universe, leading to the idea that alternate realities may contain variations of ourselves living out different lives based on different choices. This notion prompts philosophical inquiries about identity, free will, and the significance of our decisions. Additionally, the existence of a multiverse may help address some of the fine-tuning problems in cosmology. The fundamental constants of nature, such as the strength of gravity or the mass of elementary particles, appear remarkably calibrated to allow for the existence of life as we know it. If our universe is just one among many, it may be that we find ourselves in a universe conducive to life simply because there are countless other universes where conditions are not favorable for life. This perspective reframes our understanding of our own universe, suggesting that our existence may not be as improbable as it initially seems. However, the multiverse theory remains contentious. One of the main criticisms is that it may not be empirically testable, which raises concerns about its scientific legitimacy. The scientific method relies on falsifiability, meaning that a theory must be capable of being proven wrong through observation or experimentation. Since the existence of other universes might be inherently unobservable, some argue that multiverse theories drift into the realm of philosophy rather than science. This ongoing debate reflects the broader tensions between scientific inquiry and philosophical speculation. As we contemplate the mysteries of the universe, the search for extraterrestrial life stands out as one of humanity's most profound endeavors. The vastness of space, combined with the staggering number of planets and celestial bodies, has led scientists to consider the possibility that we are not alone in the universe. Efforts such as the search for extraterrestrial intelligence, SETI, employ advanced technologies to scan the cosmos for signals that may indicate intelligent life. The discovery of exoplanets, planets outside our solar system, has expanded the horizons of this search, revealing thousands of potential worlds that could harbor life. The existence of extremophiles, organisms that thrive in extreme environments on Earth, further fuels the speculation about extraterrestrial life. If life can exist in the harsh conditions of deep-sea hydrothermal vents, acidic lakes, or the frozen tundra, it raises the possibility that life could emerge on other planets with similar extreme conditions. For instance, Mars, with its history of water, or the icy moons of Jupiter and Saturn, such as Europa and Enceladus, are prime candidates for future exploration in the search for extraterrestrial organisms. The implications of discovering extraterrestrial life are profound. Such a revelation would not only reshape our understanding of biology and evolution but also challenge our philosophical and theological perspectives on humanity's place in the cosmos. If life exists beyond Earth, it invites questions about the diversity of life forms, the evolution of intelligence, and the potential for communication between species from different worlds. It could also prompt us to reconsider our responsibilities toward our planet and other life forms, emphasizing the interconnectedness of life in the universe. However, the search for extraterrestrial life also raises ethical considerations. The potential for contact with intelligent civilizations could lead to unintended consequences, ranging from cultural exchanges to conflicts over resources and ideology. It necessitates careful contemplation of how we might approach such encounters, balancing curiosity with respect for the unknown. As we venture deeper into the cosmos, the concept of time travel continues to captivate the imagination. While time travel remains a staple of science fiction, it also intersects with serious scientific inquiries into the nature of time and causality. According to Einstein's theory of relativity, time is not absolute but is influenced by relative motion and gravity. Theoretical constructs such as wormholes, hypothetical tunnels in spacetime that could connect distant points, have sparked interest in the potential for time travel. Wormholes, if they exist, could theoretically allow for shortcuts through spacetime, enabling travel between different points in the universe or even different times. However, the stability of such structures poses significant challenges, as they may collapse or require exotic forms of matter to remain open. Furthermore, the implications of time travel are laden with paradoxes, such as the famous grandfather paradox, where a time traveler could potentially alter events in the past, creating logical inconsistencies. Despite these challenges, the exploration of time travel concepts encourages deeper reflections on the nature of reality and our perception of time. It raises questions about determinism, the influence of past actions on the present, and the possibility of parallel timelines. While the practicalities of time travel may remain speculative, the philosophical inquiries it inspires contribute to our understanding of the universe and our place within it. As we conclude our exploration of the universe's mysteries, it is essential to acknowledge the role of human curiosity and creativity in our quest for knowledge. The drive to explore the cosmos reflects our inherent desire to understand the world around us, to push boundaries, and to seek meaning in existence. Our journey through the mysteries of the universe is not merely an academic pursuit, it is a reflection of our humanity. In this grand narrative, we are not just passive observers of the cosmos, we are active participants in its unfolding story. Every question we ask, every discovery we make, and every mystery we ponder contributes to the tapestry of human knowledge. The universe invites us to engage with its wonders, to marvel at its complexities, and to embrace the uncertainty that comes with exploration. Ultimately, the mysteries of the universe serve as a reminder of the beauty and wonder that exist beyond the confines of our everyday lives. They challenge us to look beyond the surface, to question our assumptions, and to appreciate the interconnectedness of all things. As we continue to unravel the secrets of the cosmos, let us carry forward the spirit of inquiry and discovery, knowing that the journey itself is as significant as the destination. In the end, the universe remains a vast and enigmatic frontier, filled with questions waiting to be asked and mysteries yearning to be explored. The pursuit of knowledge is an ever-evolving journey, and with each step we take, we illuminate the path for future generations. Together, we venture into the unknown, inspired by the possibilities that lie ahead and united by our shared quest for understanding in this magnificent cosmos we call home. As we further delve into the mysteries of the universe, we encounter the intricate phenomena of black holes. These cosmic entities, formed from the remnants of massive stars that have undergone gravitational collapse, are perhaps one of the most intriguing and misunderstood aspects of astrophysics. A black hole's gravitational pull is so strong that not even light can escape its grasp, rendering it invisible and making its study a challenge for astronomers. The formation of a black hole typically begins with a supernova, the explosive death of a star. When a massive star exhausts its nuclear fuel, it can no longer support itself against the force of gravity. The core collapses, and if the remaining mass is sufficiently large, it will form a singularity, a point of infinite density where the laws of physics, as we know them, break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape the black hole's gravitational influence. Black holes can be classified into several categories: stellar black holes, which are formed from individual stars; supermassive black holes, which reside at the centers of galaxies and can contain millions or even billions of times the mass of our Sun; and intermediate black holes, whose existence is still a topic of ongoing research. The study of these enigmatic entities challenges our understanding of physics and provides insights into the fundamental nature of the universe. One of the most significant revelations about black holes came with the detection of gravitational waves, ripples in spacetime caused by the collision of massive objects, such as merging black holes. The first direct observation of gravitational waves was made in 2015 by the LIGO, Laser Interferometer Gravitational Wave Observatory, collaboration, marking a groundbreaking moment in astrophysics. This discovery not only confirmed a prediction of Einstein's general theory of relativity, but also opened a new window into the study of the universe. The relationship between black holes and the fabric of spacetime is a captivating area of research. According to general relativity, massive objects warp the spacetime around them, creating the phenomenon we perceive as gravity. Black holes take this concept to an extreme, bending spacetime to such a degree that it creates a region where traditional understandings of time and space no longer apply. For instance, near the event horizon, time appears to slow down relative to an observer far away. This leads to intriguing implications about the nature of time itself, suggesting that time might behave differently in the presence of strong gravitational fields. Another aspect of black holes that fascinates scientists is the information paradox. When matter falls into a black hole, it seemingly vanishes, raising questions about the fate of information. According to quantum mechanics, information cannot be destroyed, leading to a clash between quantum theory and general relativity. This paradox has sparked numerous debates and research efforts, with various hypotheses proposed to resolve the issue. Some physicists suggest that information may be encoded on the event horizon, while others consider the possibility that it could be stored in a holographic form. Black holes also play a crucial role in the dynamics of galaxies. Supermassive black holes, located at the centers of most galaxies, exert significant influence on their host galaxies, affecting their formation and evolution. The interplay between the black hole and the surrounding matter can lead to the release of immense amounts of energy, observable as jets of particles shooting out at nearly the speed of light. These jets can impact star formation in the galaxy and contribute to the regulation of the interstellar medium. As we explore further, we turn our attention to the mysteries of dark matter and dark energy, two of the most significant yet elusive components of the universe. Together, they are believed to account for approximately 95% of the total mass energy content of the cosmos, yet their true nature remains shrouded in mystery. Dark matter is thought to be a form of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. The evidence for dark matter primarily comes from observations of galaxy rotation curves, gravitational lensing, and the cosmic microwave background radiation. In spiral galaxies, for example, the outer stars rotate at higher speeds than would be expected based on the visible mass alone, indicating the presence of unseen mass exerting gravitational pull. The search for dark matter candidates has led to various hypotheses, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. Despite extensive efforts, including experiments conducted deep underground and at particle accelerators, no direct detection of dark matter has yet been achieved. This has prompted the scientific community to explore alternative theories and models, including modifications to our understanding of gravity itself. Dark energy, on the other hand, is a mysterious force that appears to drive the accelerated expansion of the universe. The discovery of this acceleration, made through observations of distant supernovae in the late 1990s, revolutionized cosmology and raised profound questions about the fate of the universe. Dark energy is thought to comprise around 68% of the total energy content of the universe, yet its nature remains largely speculative. Various theories have been proposed to explain dark energy, including the cosmological constant, a term introduced by Einstein in his equations of general relativity, and dynamic fields that evolve over time. The implications of dark energy are staggering. It suggests that the universe's expansion is not only continuing but accelerating, leading to questions about the long-term future of the cosmos. Will galaxies drift further apart, ultimately leading to a big freeze scenario where stars burn out and galaxies fade into darkness? Or could there be a different fate, one that involves a big crunch, or even a big rip, where the fabric of the universe is torn apart? Exploring dark matter and dark energy invites contemplation on the very foundations of our understanding of physics. It challenges scientists to rethink their models of the universe and opens the door to new discoveries that may fundamentally reshape our understanding of existence. The mysteries surrounding these components serve as a reminder of how much remains to be uncovered in our quest to comprehend the cosmos. As we consider the cosmos in its entirety, we must also acknowledge the role of the observer. The act of observation is not merely a passive endeavor, it influences the reality being observed. This concept, rooted in quantum mechanics, suggests that the very act of measuring or observing a particle can alter its state. This leads to philosophical inquiries about the nature of reality and consciousness itself. The famous double-slit experiment illustrates this principle, demonstrating that particles can behave as both waves and particles, depending on whether they are observed. When not measured, particles appear to interfere with themselves, displaying wave-like behavior. However, when observed, they behave as individual particles. This phenomenon challenges our classical intuitions about the nature of reality, leading to the conclusion that our consciousness may play a role in shaping the universe we perceive. The relationship between consciousness and the universe is an area ripe for exploration. As we delve deeper into the mysteries of existence, we confront questions about the nature of awareness, perception, and reality itself. Philosophers and scientists alike grapple with the implications of consciousness, its origin, its place in the universe, and its potential connections to the fabric of reality. The mysteries of the universe encompass a vast array of phenomena that challenge our understanding of existence. From the enigmatic nature of black holes to the elusive properties of dark matter and dark energy, each discovery reveals new questions and invites further exploration. The interplay between science, philosophy, and the quest for knowledge reflects the profound human desire to understand our place in the cosmos. As we continue to seek answers to these mysteries, we contribute to the unfolding narrative of our universe, a narrative rich with complexity, wonder, and an ever-deepening appreciation for the unknown. Ultimately, the mysteries of the universe serve as a reminder of the beauty and intricacy of existence. They inspire curiosity, creativity, and a relentless pursuit of understanding. As we gaze into the night sky, we are reminded that we are part of something much larger than ourselves, a cosmic tapestry woven with threads of mystery, wonder, and the boundless potential for discovery. As we delve deeper into the vast expanse of the universe, we encounter yet more enigmas that challenge our understanding. One such mystery is the concept of the multiverse. The idea that our universe may not be the only one is both thrilling and perplexing. The multiverse theory posits that there could be an infinite number of universes, each with its own distinct physical laws, constants, and initial conditions. This notion stems from various branches of theoretical physics, including quantum mechanics and cosmological inflation. Quantum mechanics introduces the idea of superposition, where particles exist in multiple states simultaneously until observed. This leads to the interpretation that every possible outcome of a quantum event occurs, resulting in a branching of realities. In this framework, each decision we make or event that occurs could create a new universe, where alternate outcomes are realized. This interpretation, often referred to as the many worlds interpretation, invites us to ponder the implications of choices and alternate realities. Cosmological inflation, a theory that describes the rapid expansion of the universe just after the Big Bang, also supports the multiverse hypothesis. According to this theory, different regions of space can stop inflating at different times, leading to the creation of bubble universes. Each bubble can have its own unique set of physical laws and constants, resulting in a vast array of universes within a greater multiverse. This raises profound questions about the nature of reality and our place within it. The multiverse theory, while captivating, also faces challenges. It often seems untestable, leading to debates about its scientific validity. Critics argue that if other universes exist beyond our observable reach, they may remain forever beyond our ability to detect them, placing the concept in the realm of speculation rather than empirical science. Nevertheless, the multiverse remains a popular topic of discussion among physicists and cosmologists, igniting imagination and inspiring further research into the fundamental nature of reality. As we ponder the mysteries of the cosmos, we also confront the enigma of time itself. time, a fundamental aspect of our experience, appears to flow in one direction, from past to present to future. Yet, the nature of time is far from straightforward. In classical physics, time is treated as a linear, absolute entity. However, in the realm of relativity, time becomes intertwined with space, forming the fabric of spacetime. According to Einstein's theory of relativity, time is relative. It can be experienced differently depending on one's velocity and gravitational field. For instance, time passes more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. This has been experimentally confirmed through precise measurements, illustrating that the ticking of a clock can vary based on its position in a gravitational field. Such revelations lead to profound implications for our understanding of reality, suggesting that time is not a constant but rather a malleable dimension influenced by the universe's dynamics. The concept of time also raises questions about its ultimate nature. Is time fundamental, an intrinsic part of the universe, or is it an emergent phenomenon arising from more fundamental processes? Some physicists speculate that time may not exist at the quantum level, where particles behave in ways that seem to defy our classical understanding. In this view, time could be a macroscopic illusion, a construct that emerges from the underlying physics of the universe. The idea of time travel further complicates our understanding of time. While time travel is a popular theme in science fiction, theoretical physics suggests that it may not be entirely impossible. Solutions to the equations of general relativity, such as closed time-like curves, propose scenarios where travel to the past could occur. However, these theories often involve exotic conditions, such as the presence of negative energy or hypothetical constructs like wormholes. Wormholes, a topic we touched upon earlier, serve as fascinating theoretical shortcuts through spacetime. They could potentially connect distant regions of the universe or even different points in time. However, the stability and practical feasibility of traversable wormholes remain subjects of intense debate. The concept invites contemplation about the fabric of reality and the possibilities it may hold. In the quest to understand the universe, we cannot overlook the significance of dark energy and its influence on cosmic evolution. The discovery of dark energy has reshaped our understanding of the universe's fate. As previously mentioned, dark energy is believed to drive the accelerated expansion of the cosmos, leading to questions about the ultimate destiny of galaxies, stars, and matter. One potential scenario is the Big Freeze, where the universe continues to expand indefinitely. In this model, galaxies drift farther apart, stars exhaust their nuclear fuel, and matter becomes increasingly sparse. Over trillions of years, the universe could cool to a state of near absolute zero, with only remnants of stars and black holes remaining. This end state raises philosophical questions about the nature of existence and the potential for life in a dark, cold universe. Alternatively, some theories propose the possibility of a Big Crunch, where the expansion of the universe eventually halts and reverses, leading to a collapse. In this scenario, galaxies and matter would converge, culminating in a singularity. This cyclical model raises questions about the nature of time and existence. Could the universe undergo infinite cycles of birth and rebirth? The concept of entropy also plays a crucial role in these discussions. Entropy, a measure of disorder, tends to increase over time in isolated systems, a principle known as the second law of thermodynamics. In the context of the universe, this means that as time progresses, energy becomes increasingly dispersed, leading to a state of maximum entropy where no useful energy remains. The implications of entropy are profound, suggesting that the universe is gradually moving toward a state of thermal equilibrium. As we contemplate the mysteries of the universe, we also encounter the question of existence itself. Why does the universe exist? What is its purpose, if any? Philosophers, scientists, and theologians have grappled with these questions for centuries, often leading to more questions than answers. The nature of existence touches upon deep philosophical inquiries about the meaning of life, the nature of consciousness, and the fabric of reality. In the search for answers, we must also confront the role of human perception in shaping our understanding of the universe. Our senses provide us with a limited perspective of reality, filtered through our biology and cognitive frameworks. This invites contemplation about the nature of knowledge and the limitations of human understanding. What truths lie beyond our current comprehension? Are there aspects of the universe that will forever elude our grasp? The exploration of the cosmos also brings to light the interconnectedness of all things. From the tiniest subatomic particles to the grandest cosmic structures, the universe operates as a complex web of interactions. The principles of physics govern the behavior of matter and energy, revealing a tapestry of relationships that shape the cosmos. This interconnectedness invites a holistic perspective, prompting us to consider the implications of our actions on a universal scale. In this context, the search for extraterrestrial life emerges as a captivating avenue of inquiry. The vastness of the universe, with its billions of galaxies and countless stars, raises the tantalizing possibility that life may exist beyond our planet. Efforts to explore Mars, the icy moons of Jupiter and Saturn, and exoplanets' inhabitable zones reflect humanity's desire to understand its place in the cosmos. The search for extraterrestrial intelligence, SETI, aims to detect signals from other civilizations, further expanding our understanding of existence. The prospect of encountering alien life raises profound questions about the nature of consciousness, communication, and the potential for shared experiences across the cosmos. How would our understanding of ourselves change if we were to discover intelligent beings elsewhere? Would we find common ground in our search for meaning, or would the differences challenge our perspectives? Ultimately, the mysteries of the universe beckon us to embrace curiosity, wonder, and exploration. They remind us of the beauty and complexity of existence, and the importance of asking questions. As we stand at the intersection of science, philosophy, and spirituality, we are compelled to seek answers to the enigmas that surround us. Each discovery, each breakthrough, reveals new layers of understanding, illuminating the path forward in our quest for knowledge. As we conclude this exploration of the mysteries of the universe, we are left with a sense of awe and reverence for the cosmos. It is a realm filled with questions that challenge our understanding, inviting us to ponder our place in the grand tapestry of existence. The universe, with all its wonders and enigmas, serves as a reminder of the beauty of discovery and the boundless potential for understanding that lies ahead. Our journey into the cosmos is far from over. It is a continuous quest that will inspire generations to come. In a world that often feels chaotic and fragmented, the mysteries of the universe provide a sense of unity and purpose. They invite us to look beyond ourselves and contemplate the vastness of existence, reminding us that we are all part of a grand narrative that transcends time and space. As we gaze up at the stars, we are reminded that we are explorers in a boundless universe, and our journey of discovery is just beginning. In essence, the mysteries of the universe challenge us to think deeply about our existence, our place in the cosmos, and the nature of reality itself. They encourage us to embrace uncertainty, to ask questions, and to seek knowledge in the face of the unknown. Through exploration, inquiry, and imagination, we can unlock the secrets of the universe, shedding light on the profound mysteries that have captivated humanity for millennia. The universe is not merely a collection of stars and galaxies. It is a dynamic and ever-evolving tapestry of existence that invites us to explore its depths. As we continue our journey, let us remain open to the wonders of the cosmos, embracing the mysteries that inspire us and the questions that propel us forward into the unknown. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.